So today we're going to cover Chapter 4, Section 1. Today we're going to look at rational functions and asymptotes. So today most of our focus is going to be on learning how to find a horizontal and a vertical asymptote when we have a rational function. Now we've already seen asymptotes when we graphed the hyperbolas. Those were the linear functions. For this section, they're actually just going to be a vertical or a horizontal line. Later on, what we're going to see is sometimes our graph will have a slant asymptote, and that'll be, well, in order to find that, we're going to use long division. So over here, this function that's listed here, this is a rational function. Remember, rational is a fraction. By definition, rational is any number that can be written as a over b or in fraction form. Now, one thing to remember why these asymptotes happen is if you think about the domain of a function, remember when we covered domain and range, the domain, you should always start out by thinking that the domain is all real numbers. Then the only time it was not all real numbers is when there was a fraction and you had a variable in the denominator, because remember, you can never have a zero in the bottom of a fraction, then it becomes undefined. And then the other case that we had to check was for radicals, square roots. So in this case, this function that's listed here, 1 over x, the domain here is all real numbers except when x equals 0. So x cannot equal 0. Notice I have an asymptote. Notice how this is actually a hyperbola graph. But notice here, right here, this is my asymptote. Notice my graph skims along this this y-axis, which is x equals 0. It will never touch this y-axis. It actually also has a horizontal asymptote right here for the x-axis. We're going to learn how to find the equations for these horizontal and vertical asymptotes in today's lesson. We're not going to be graphing anything today. Only thing we're doing today is to locate these asymptotes. Now, just a little bit of tie into maybe what is sort of leading into calculus. Over here, what this is saying as f of x increases without bound, meaning it's going to infinity as x approaches 0 from the right. And then this would be as the function f of x approaches infinity as x approaches 0 from the left. Little terminology here tied to calculus. You don't need to know this. This is just a little bit of tie-in getting us into what's to come. And then over here, this is as your function f of x approaches 0 as x approaches infinity or without bound. That's what this means. Or here as your function equals infinity, or as it approaches 0 as x approaches negative infinity. So going to the left without bound. But again, you don't need to know this. This is just means that your asymptote's going to go forever in both directions. So here in this picture, though, what'll be important is that this has a vertical asymptote. Actually, let me do it in the color that I drew it. It's got a vertical asymptote at x equals 0, and it's got a horizontal asymptote at y equals 0. And we're going to learn how to find these. And you're just going to have to memorize the rules on how to find them. And now these are for rational functions. So in order to locate an asymptote or a hole in the graph, there's some rules you're going to follow. So for a vertical asymptote, what we're going to do is take the denominator of our rational function and set it equal to 0. And that would give us the equation for our vertical asymptote. This is going to be the line that our graph is not going to cross. It'll skim along it and get really close to it. So the vertical asymptote is easy. You just set the denominator equal to 0. The horizontal asymptote has 3 different scenarios. Generally, the graph will not cross this horizontal asymptote, but it can. In a few cases, it may cross over the asymptote. But for the most part, once you draw in these asymptotes, that's going to be like the wall or the guide for your graph. Now, what's going to be important here is that you have your equation in standard form, or from the biggest exponent down to the smallest. So for example, you'd have to put it in order. So x to the third plus x squared, and let's say it's minus a 2x minus 5. So it needs to be in order from the biggest exponent down to the constant. This, what we need to look at for the horizontal asymptote, is the degree of my function. The degree here is based on the largest exponent. So this function here, if this was f of x, would have a degree of 3. Now, let's say I have a function that says f of x equals x plus 1. Remember, this has an assumed power of 1 on the x, so this would have a degree of 1. If you have just a function, let's say it's f of x equals 5. Whenever it's just a constant, the degree equals 0. So a constant has a degree of 0. What's important is being able to identify the degree of the numerator and the denominator in order to figure out our horizontal asymptote. So let's go ahead and see the 3 different scenarios. So once it's in standard form and you have it from the biggest exponent down to the constant, what we're going to do is we're going to, in this explanation here, n is the degree of the numerator, and m is going to be considered the degree of the denominator. So our first scenario here is when the numerator degree, so this is the first scenario, so when the numerator degree, the top degree, is smaller, so when n is less than m, then your horizontal asymptote is just located at y equals 0. So when the top degree is smaller than the bottom, then it's just y equals 0. You don't have to do any math. You're just looking at the degrees. If the top is smaller, if the numerator is smaller than the bottom degree, the horizontal asymptote is located at y equals 0, which is the x-axis. The next scenario is when the top is bigger. So when the top degree is bigger, then you're going to say that there is no horizontal asymptote. The top is bigger. However, if the top is 1 more than the bottom, then what's going to happen is it's not going to be horizontal, it's going to be a slant. So it's still no horizontal. But if the top is 1 more than the bottom, you will have a slant asymptote. And to find this slant asymptote, we're going to be doing long division. But we're not going to cover that today. Today we're only looking for horizontal and vertical. And then the last scenario is when the 2 degrees are equal. Then what you're going to do is take the leading coefficient of the numerator and put it over the leading coefficient of the denominator. That's when the 2 degrees are equal. And we're going to see some plenty of examples of this. Now, sometimes our graph is going to have a hole in it. So a hole exists if you can simplify the function by crossing through a factor in the numerator and the denominator. Then the hole is going to be located at that ordered pair. So for example, let's say my hole was at the ordered pair 2, 3. So what your graph could look like is that it would come here, it would hit the hole at the ordered pair 2, 3, and then it would keep going. So it's going to be like a break in your graph. It'll be a little circle. And we're going to learn how to find these holes, because what we're going to be doing is factoring the numerator and the denominator. And then whatever factors cancel, that's where our hole is going to be located. So let's try to apply all of these instructions. And we're just going to do a bunch of examples. Try examples. Now, this 1, 2, and 3 here only want horizontal. Remember, we have the 3 scenarios. When the top is going to be smaller, then we know it's y equals 0. When the top degree is bigger, then there's no horizontal asymptote. And then when they're equal, we're going to use the coefficients. Now, remember, you need to first check to see if it's in order from the biggest exponent down. Now, my first one's already set. Remember, the degree of a constant, so this is the degrees. So the degree of a constant is 0. The degree of my denominator here, I can assume a 1. So the degrees are 0 over 1. The top is smaller. It's got the smaller degree. When the top has the smaller degree, all we have to memorize is the horizontal asymptote is y equals 0. So when the top is the smaller degree, you would just write y equals 0. And again, remember, this is going to be the x-axis when we start graphing these. Right now, we're not graphing. We're just finding the location of the horizontal asymptote. Whenever I abbreviate horizontal asymptote in these notes, I'm just going to put HA. Because the degree of a constant, the constant always has a degree of 0. The x has an assumed 1. Its power is 1, so this degree is 1. So 0 is smaller than 1, so this is why the horizontal asymptote is located at y equals. Don't get confused with powers and degrees. So a constant's degree is 0. The exponent on the 3 is a 1. Now, technically, when it's a variable, the degree and the power are the same thing. But for just a single number, a constant, the degree is 0. Pretty good? Let's try the next one. It is in standard form. It's got the x and then it's got the constant. This one has a degree of 1. This has a degree of 1. You're looking at the power on the x on the variable. So the 2 degrees are 1 over 1. When the degrees are the same, this is where I'm going to use the coefficients. So the coefficients that I'm using are the coefficient of the numerator over the coefficient of the denominator. And it's y equals. All of these horizontal asymptotes are going to be y equals. So when the degrees are the same, we're just using the coefficients. So the horizontal asymptote here is located at y equals 2/3. It's going to be that horizontal line going through 2/3. Let's try the next one. So the degree of the numerator is 2. The degree of the denominator is 1. The top is bigger. So you're going to write that there is no horizontal asymptote. Since the top is actually one bigger, there's actually going to be a slant asymptote, but we're going to learn how to find that later on. So if it asks you to list horizontal asymptote and vertical, horizontal, you would put none. Again, to find this slant asymptote, we're going to be using long division. And we're going to cover that later on, but not today. The next examples, we're actually going to find both now. We're going to find both the vertical and the horizontal. So let's go through and let's just first go ahead and find all the horizontals first. Then we'll go back and do all the verticals. So let's do the horizontals first. So again, for the horizontals, we look at the degrees. So this has a degree of 1. This has a degree of 2. So again, I'm looking at the powers to determine the degree. So that's 1 and that's a 2. When the top is smaller, so the top is smaller, so this tells me my horizontal asymptote is going to be located at y equals 0. Now let me just go through. I'm going to do all 4 horizontal first. Then I'll go back and do the verticals. For number 2, again, I'm looking at the degrees. So for number 2, the degree of the top is 2. The degree of the bottom is 2. When the degrees are the same, I'm going to be using the coefficients. So the coefficients I'm using are this 2, and then I can assume a 1 here. So my horizontal asymptote is going to be y equals 2 over 1, which just is y equals 2. For number 3, again, make sure it's in standard form. It is. So again, same thing here. My degree of the top is 2. My degree of the bottom is 2. They're the same. I'm using the coefficients. So I end up with y equals 1 over 1. And my horizontal asymptote is y equals 1. Last one, same thing. The degrees are the same. 2 over 2. So they're the same. I'm using the coefficients. So y equals 3 over 1, which is y equals 3. So those are all the horizontals. Now let me go back and let's get the verticals now. Now, for the vertical, we need to see if we can factor anything and simplify the fraction first. Now, for the first one, 2x over 3x squared plus 1, I can't simplify this rational function, so I'm just going to go ahead and for the vertical, you set the denominator equal to 0. So for my vertical asymptote, 3x squared plus 1 equals 0. Subtract 1. 3x squared equals negative 1. Divide by 3. I get x squared equals negative 1/3. Square root both sides. And x is equal to plus and minus I 1 over square root 3. I don't want any imaginaries. So when that's the case, you would say that there is no real solution here. So no vertical asymptote here. So no imaginary asymptotes. We're not graphing imaginary numbers. So this one, the vertical asymptote would be none. Let's try the next one. Now, remember back when we simplified rational functions, 2x squared over x squared minus 1, remember this is attached. I can't simplify the x squareds here. So this is already simplified. I can actually factor the denominator, but it doesn't really, I don't have to. Whenever you're trying to find a vertical asymptote, before you can set the denominator equal to 0, you must factor and see if something will cancel first. You're setting the simplified function equal to 0 from the denominator. So the numerator, x squared plus x minus 2, will factor into x plus 2 and x minus 1. The denominator factors into x plus 2 and x minus 3. Notice that my x plus 2's cancel. So my simplified function, f of x, is equal to x minus 1 over x minus 3. Now that I've simplified it, to find my vertical asymptote, I'm going to set the denominator equal to 0. And I have a vertical asymptote at x equals 3. Now, because I could factor this and cancel a factor, I have a hole. The hole is going to occur at the factor that was canceled. So I'm going to take the x plus 2 that I canceled out. So this is coming from when I simplified. Set it equal to 0. Minus 2. Now, remember, this hole is an order pair. By setting that denominator equal to 0, I've just found the x of the hole. I now have to find the y. I'm going to take this x and I'm going to plug it in to the simplified function. Because remember, this f of x equals x minus 1 over x minus 3. F of x is a fancy way of saying y equals. So now I'm going to take out both of the x's, and I'm going to replace it with negative 2 to get my y value. So negative 2 minus 1, negative 2 minus 3 gives me y equals negative 3 over negative 5. Negative divided by a negative, and my y value is positive 3/5. So my hole is located at the order pair negative 2, positive 3/5. So if you were to graph this rational function, you're going to have a little open circle at this order pair. But again, we're not graphing anything tonight. Tonight's homework is only finding vertical and horizontal asymptotes. Let's try number 4. Or was that number 4? Nope, number 4 is here. Okay, so number 4, it's this one. So I already found the horizontal. It was y equals 3. Now, for this one again, before you can even set that denominator equal to 0, to find the vertical, you have to factor first. So I'm going to factor the numerator. It will factor into, and again, whatever method you want to use for factoring, whether you use guess and test, factor by grouping, it's totally up to you. The numerator, the 3x squared plus 7x minus 6, will factor into 3x minus 2 times x plus 3. The denominator is going to factor into x plus 1 and x plus 3. Again, I want to simplify this. The x plus 3's cancel. So my simplified function is now 3x minus 2 over x plus 1. To find the vertical asymptote, you set the denominator equal to 0. I have a vertical asymptote located at x equals -1. Because I had a factor that canceled, I have a hole. My hole is located at the factor that canceled, so the x plus 3 equals 0. X equals -3. Remember, the hole is an ordered pair. So now I take that x equals -3, and I'm going to plug it in to my simplified function. So I'm plugging it into y equals 3x minus 2 over x plus 1. Again, I'm plugging in -3 for each of these x's. I'm trying to find the y of the ordered pair. So y equals 3 times -3 minus 2, -3 plus 1, -9 minus 2 over -2, which gives me -11 over -2, simplifies to positive. Yes, Bradley. All right, so my ordered pair for my hole is located at -3, positive 11 over 2. That's the location of the hole. So this is my vertical asymptote, my hole, and then the horizontal I found way at the beginning. Let's try 4 more examples doing exactly the same thing. And that would conclude the notes on 4.1. Okay, so let's do all the horizontals first. So for the horizontal, we look at the degree. Remember to fix it and make sure that it's in standard form. So if I fix this, it's going to end up being -7x plus 3 over 2x plus 3. So for the horizontal, we look at the degree. The degree of the first one is 1. The degree of the second one is 1. When the degrees are the same, we use the coefficient. So the coefficient here is -7 and +2. So y equals -7 over 2. Both of the degrees are the same. So that's your horizontal. Let's try number 6 is horizontal. So the degree of the top is 1. The degree of the bottom is 2. The top is smaller. So when the top is smaller, your horizontal asymptote is located at y equals 0. You just memorize it. Let's do the next one. It's in standard form. So the degree of the top is 2. Degree of the bottom is 2. They're the same. So again, I'm going to use coefficients. So I can assume that this is a 1 and a 1. So the horizontal asymptote is located at 1 over 1, which is just y equals 1. Same thing on the next one. Degrees are the same, 2 over 2. So when they're the same, I'm going to use the coefficients. So y equals 1 over 2, and that is my horizontal asymptote. Now for the verticals, we need to see if we can simplify first. If we can't simplify, then we just set the denominator equal to 0. So back at number 5, remember I can't cancel those 3's because again, remember these are attached. So nothing to simplify. So for the vertical, I'm just going to set 2x plus 3 equal to 0 minus the 3. 2x equals negative 3. Divide by 2. And my vertical asymptote is located at x equals negative 3 over 2. The next one can be factored. I can factor the denominator. So my function is f of x is equal to x plus 3 over x squared minus 9. I can factor that denominator into x plus 3, x minus 3. I can look for things to simplify. The x plus 3's cancel. Remember, when this cancels, a 1 is left behind. So my simplified function is f of x is equal to 1 over x minus 3. I now take the denominator, set it equal to 0 to get my vertical asymptote. I have a vertical asymptote located at x equals 3. This also has a hole. So because I was able to cancel a factor, I have a hole that's located. Set the factor that was canceled equal to 0. This will give me the x of my order pair. And then to find the y, you're going to take the simplified function, and I'm plugging in negative 3 for the x. So y equals negative 3 minus 3. So the y of my hole is negative 1/6. So my hole is located at negative 3, negative 1/6. Because again, you put these two together and it makes the order pair. Number 7, we need to factor first. I can factor the numerator, difference of two squares, x minus 2, x plus 2. The denominator is going to factor into x minus 1 and x minus 2. My x minus 2's will cancel. So my simplified function first, f of x is equal to x plus 2 over x minus 1. For the vertical asymptote, we set the simplified function denominator equal to 0. Add 1. My vertical asymptote is located at x equals 1. Because I canceled a factor, I have a hole located at x minus 2 equals 0. Add the 2. The x of the order pair of the hole is 2. I now take the simplified function, and I'm going to plug in x equals 2. So x plus 2 over x minus 1. Again, you're plugging in this number for both x's. So y equals 2 plus 2 over 2 minus 1, 4 over 1. So the y of your order pair is 4. So your hole is located at 2, 4. Last example, exactly the same thing. We've already found the horizontal. Let's find the vertical. Factor first. I can factor the numerator into x plus 2, x minus 1. The denominator will factor into 2x plus 1 times x plus 2. Again, whatever technique you want to use for factoring, I don't care. Whether it's grouping, whether it's not. And I just did something wrong. This should be an x plus 2. This should be x plus 2. Because again, you could always quickly FOIL and make sure it does go back. All right, so now again, to simplify it, I need to see what I can cancel. I can cancel the x plus 2's. So my simplified function is going to be f of x is equal to x minus 1 over 2x plus 1. To find the vertical asymptote, take the simplified function's denominator, set it equal to 0. Subtract 1, 2x equals negative 1, divide by 2, and your vertical asymptote is located at x equals negative half. Now again, it's got a hole because I had a factor that canceled. Set that factor equal to 0. This just gave me the x of my holes order pair. Again, take that x value, plug it into the simplified function. So the x minus 1 over 2x plus 1, plug in negative 2, follow PEMDAS, negative 3, this becomes 2 plus 1, and then I end up with once I multiply here, I messed up here, hold on. This should be, let me fix here. Sorry, this should be a positive 2. Hold on, let me fix this denominator. Plugged it in wrong. Okay, so I'm doing 2 times negative 2 minus 1. Gives me negative 4, there should be a plus. Plus 1 gives me negative 3. Negative 3 divided by negative 3 is positive 1. So my hole is located at the order pair, negative 2, positive 1.